Hi, this is Jeff Evans from Evans Performance Academy. We're going to be taking a look at some basics with our PC Link software so you can get started with your Link G5 or G4X system. Without further wait, let's jump in to check this out. Okay, so let's get started. We're going to be taking a look at understanding the differences between our traditional and model mode in this training module. Now, we're going to be exploring these two topics because this is one of the very first things we really have to decide in order to program and set up our Link G5 or G4X systems. Are we going to be tuning in traditional mode, which is a injection time-based model, or are we going to be tuning in the model mode, which is going to be volumetric efficiency, air mass based calibrating and tuning? They're very unique in terms of how they work and how they calibrate. So we want to make sure we're picking the correct one, because if you switch it, it's going to require retuning a lot of the fuel tables, main fuel table, a lot of the sub compensation tables. It's important that we know which one we want to work with first so we can choose that, and then we can set everything else up based on that model mode that we're working with or traditional mode. All right, let's jump in here and take a look at first where we're going to be selecting and setting up traditional or model mode, and then we're going to break down understanding the key details, the bigger picture of what these both represent. Now, we are going to be using the Excel spreadsheet calculator that I provided in the training course folder. If I go ahead and minimize this real quick and we jump in here, I actually have that calculator open here. We're going to take a look. I have this open on my desktop, G5 course packet, and then we can find in here G5 master training course calculator. That's what I do have open, and we'll be looking at this in this training module to get a better idea as to what's going on with this. I find a little bit easier to describe things using the calculator and being able to just demonstrate a few different key details here as we're discussing the model and the traditional mode. Let's jump back in here to our G5 software. Okay, so we are on the basics page in the layout I provided with the training course. We've talked about this layout and what it represents. This is what I'm going to be using throughout the entire training course. So on the basics page, I have everything that is going to give us the essential details for calibrating and tuning the very basic programming parameters. These are going to be things like our injector latency and short pulse width data. That goes with the injector characterization. We have our ignition coil dwell. So this is going to be specific to the coils that we're using, so we can command the dwell properly so we get proper spark. We're going to be setting up things like our number of cylinders and our firing order. Then we're going to find we have an area here, fuel main. This is where we set up our fuel details. So if we look at the injection mode, we have some options in here. We have single point group, multi-point group, sequential, group stage, sequential staged, direct injection port. Right now, just to illustrate this and just keep it as simple as possible, we're going to grab sequential style injection. This is typically what you're going to select with the link. Very rarely you'll be going in and selecting some of these other options. We will have a dedicated tutorial talking about all of the options in here. What I want to focus on now is our fuel mode that we're going to be working in, either traditional or model mode. All right, let's click OK here so we get something to get going with the tutorial. Okay, now we can see within our fuel main area here, we have fuel equation mode. Here, we're either going to be choosing traditional or model. Now, we also have a third option, model multi-fuel. What this is going to allow us to do is in the model or volumetric efficiency based calibrating and tuning option, we can work with flex fuel, which is the multi-fuel option. We're just going to be discussing traditional model for right now. When we get into setting up flex fuel and doing all of that, we'll talk about the model multi-fuel and how to configure and set all that up so you have things properly dialed in for a flex fuel based tune. For right now, let's focus on just talking about, again, traditional model. I'm going to select traditional here, click OK, and now we're going to be left with all of the programming details that we find down here below. Now, I am not going to get into every single detail in this training module. I want to have the bigger picture taken away here so you understand the key differences between the traditional and model mode. When we're talking about our traditional option here, we are going to find that we are working in an injector pulse width based model. What does that actually mean? Well, it's a pretty simple calculation that goes on here. We're going to find that we have our main fuel table. So if we bump in here to our fuel page, this is our main fuel table. We can see it's based on manifold gauge pressure versus, in this case, engine speed. This is the traditional way we'll find the tables configured. Now the values in the table are going to be a percentage. We can see here fuel table percent. This percentage that's populated in the table at any given cell point is going to be used in the equation to calculate an injector pulse width in the traditional mode. So let's take a step back here. Let's go to basics. So we're going to find here that we have a master fuel option. The master fuel right now is set to 15 milliseconds. The way this is going to work in the traditional strategy is going to be we take the master fuel trim, we multiply it by the percentage value in the table, so wherever we're operating at, this is going to be based on map pressure baro, it's a relationship there. Engine speed, so we see here we could be at any of these points of operation. Let's just assume we're right here. So it's going to say 15 milliseconds multiplied by 68% or 0.68, and then it's going to be further multiplied by whatever the map pressure reading is going to be, and that's going to be in units of kPa. And what we would find in that case is that we take the map pressure reading and we divide it by 100. So we're multiplying, going back here, the master fuel multiplied by the percentage from the fuel table multiplied by the map pressure reading. All of that combined gives us the injector pulse width that we're going to command to the fuel injector to open and close to spray the fuel into the engine. It's extremely simple. There's not other factors taken into consideration, such as engine displacement or the injector flow. When we're scaling things and we're setting everything up, our master fuel option here, along with the values we place in the fuel table, will allow us to scale up or down the pulse width to compensate for whatever size injector we have installed in our fuel system. So this is going to be a much more simplistic way to calibrate and tune in the traditional mode compared to the model mode, as we're going to discuss in a little bit. That's more math-based. There's a lot more going on to calculate the injector pulse width. Now, just to demonstrate this so we can see this a little bit easier in breaking down the traditional mode, let's jump into the Excel spreadsheet calculator. I actually have a pretty decent spreadsheet here. It's going to illustrate this, make a little bit more sense of the traditional mode. Jumping here to the traditional page in our spreadsheet, we're going to find here that we can go ahead, and this is a generic fuel table here. So I have a generic fuel table. We see our axes here, MGP versus engine speed. That's in the blue. We can change any of these values. So anything in the blue in the spreadsheet, we can change. Anything in the green, the yellow, or the orange is a calculated amount. So let's discuss this real quick. So what we can see here is that the master fuel trim is an overall scaler. It is going to drive up or down that injector pulse width calculation. The values in the table, again, are part of that equation, and our map pressure is also part of that equation. Now, what we can find, and what I wanted to illustrate with this Excel spreadsheet calculator, is anything here in the green, that's a calculated amount, this is the total pulse width. What that means is it's going and taking a look at the master fuel trim, it's going in and multiplying it based on the manifold pressure, and it's also then going in and multiplying it based on our fuel table value. What we're left with here is this pulse width. This is in milliseconds. This is how much the injector is open or closed. Then we find here in this particular yellow table, this is injector duty cycle. This is going to be how much of the total injector flow we're using at any given time. Finally, we'll find down here below in the orange, this is the total flywheel horsepower that we're going to be able to fuel based on what we have here in our main fuel table in conjunction with the master fuel trim value and the map pressure reading. So we can see this is going to be kind of a cascading effect. Let's go here and just change the master fuel. I'll go here and change it from a value of 4 to 8 milliseconds. Now, what that's going to do is recalculate the pulse width. It's going to essentially double the pulse width, essentially. And then the duty cycle here is going to bump up. Now, the way I have this set up in this spreadsheet, and again, we're going to be drawing on this and talking about it heavily in another training tutorial talking about the traditional mode and really trying to break things down. Anything that's highlighted in the red is when the injector duty cycle is going to be a concern. So this can, as we're scaling and set everything up here, we can get an idea if the way we're scaling our master fuel trim is a problem or not. It's simple. It's very straightforward to calibrate and tune in the traditional mode. Again, it's going to be essentially a way that we can directly calculate the pulse width and command that to the link to pulse the injector to get get the proper flow into the engine. It does require the same amount of tuning as our model VE mode, and there are the advantage is that it's simplistic. We can go in and change a few different parameters in order to get the results that we're after. So let's now talk about the model mode. So that's going to be switching things up here in our G5. Let's go back here to the basics. In our model mode, we're going to have this option. Go back to traditional, go into model. We're going to find that we have to enter in more details. We can see here that we have to enter in the engine capacity. We also have to go into the injector setup and provide the link what the injectors flow and what the actual fuel pressures at of what the injectors are rated in terms of flow. So when you look at an injector data sheet, you're going to have to enter in the flow rate at what base pressure that flow rate is given. And then we're going to have to provide other details such as number of cylinders, engine displacement, engine capacity, same thing. And then we also have to establish a few different things. Fuel system type, whether it's going to be a MAP pressure system, rising rate 1-to-1 ratio. So your fuel pressure regulator is set up with a vacuum line to the intake manifold, or returnless. So if you don't have a return line and your fuel pressure isn't changing at that 1-to-1 ratio, so fuel pressure isn't changing to manifold pressure. Or we could have fuel pressure sensor. This is the most ideal way to control within the Link programming when we're dealing with a model mode. Fuel pressure sensor feeds back into the modeling and it adjusts the injector pulse width based on any fuel pressure changes. So it's a really nice way to have things configured. But let's assume we're map referenced here. Let's click OK. Now, it uses some math modeling to figure out what the injector pulse width should be, but it does it in a very math model way, where before the traditional mode, we had a master fuel trim value, we move it up or down, we can move our fuel table values up and down, and essentially we can scale things out and getting our fueling delivery correct pretty quickly to the engine. Now in the model mode, things are math based, as I was mentioning. Now, how do we actually configure and work with all these parameters? Now there's an equation that's going to give us what's known as the estimated air mass. So because we're in a speed density system here, meaning we don't have a mass airflow sensor measuring how much airflow is coming into the engine, we're going to have a map pressure sensor so we can determine the manifold pressure, but we need to tell the Link in a modeled mode how much air mass is entering the engine. So air mass is a combination of both airflow and air density. Now, how do we do that? Well, we're going to be using a pretty simple equation, which is estimated air mass is equal to the map pressure sensor reading multiplied by volume per cylinder. So it's literally the engine displacement divided by number of cylinders. Then we divide that by 287. We multiply that by the charge temperature. So that's the density portion. So we're accounting for air density entering the engine. And then finally, all of that's multiplied by a volumetric efficiency percent. And that's actually what we represent here in the table. How much cylinder filling is happening in the engine at any given time. Again, I'm not going to go through the math on this one, but what we'll find is that if we have everything entered correctly here in our basic section, so it's the number of cylinders, engine displacement, all the injector information, so all of that's entered correctly, and we have our VE table dialed in here, we will find that we can calculate an accurate estimated air mass. Now, it's only part of the equation that goes on here with the model mode. Then we need to calculate a fuel mass. So fuel mass is how much fuel we need to inject into the engine through the injectors based on how much air mass we have coming in. It's a pretty simple equation. We have fuel mass is equal to air mass divided by target air fuel. Now, we know the estimated air mass based on the factors that we discussed in the basic section, plus what we have in the table here. So that gives us the air mass. The target air fuel is going to be our target lambda value multiplied here by the stoichiometric ratio of the fuel. So we multiply those together. That gives us target air fuel. We know the air mass. We know our target air fuel. Then we can calculate fuel mass. Now, a couple additional things here. We convert fuel mass into an injector pulse width, so the base pulse width, specifying the injector flow and the base pressure we're operating at. So that gives us the base pulse width. Then we add the injector data onto that. So the pulse width is going to grow a little bit. that's allowing us to characterize the response of the injector. We're going to get into what all this means at a later point in time. The takeaway here is that the model mode is going to be essentially factoring in and calculating your charge temp or air density within the modeling. So as we move our VE values up and down in the table here, we're telling the link that we're moving more or less air. It's going to give us more or less fuel based on that. So that's pretty simple. But all the other math modeling that goes on in the background, we'll find is a benefit because we can essentially take a volumetric efficiency table, for example, from one engine, and we can bring it in and use it for another engine as long as we've entered in the basic details here. So we could take it from a 4-cylinder, we could apply it to an 8-cylinder engine, and it will at least start and run the engine pretty close. With the traditional mode, it is a lot more setup work in terms of actually getting the fuel table worked out between the master fuel trim value and what we're commanding in the table here. A little bit more legwork to get that sorted out, but it does give us a far more simplistic way to actually bring the pulse width to the injector and bring the fuel flow into the engine. So we have a more complex math modeled system that has a decent amount of benefits to it. And then we have the traditional mode, which really dumbs things down and keeps things extremely simple. If you're familiar with other standalone systems, the traditional mode is what you would find on an AEM Series 1 or Series 2 box. Those were injector pulse width based system. And then if looking at the AEM products, they moved to AEM Infinity, that was a volumetric efficiency air mass modeled system. So that would be the equivalent here of a modeled mode. That's the difference in terms of what we have to select for here. Now, most times I'm going to be choosing the modeled mode because again, it has a lot of advantages as we're going to be discussing throughout the training course. But if you wanted to keep things extremely simple, the traditional mode works extremely well, and I do use it from time to time on certain applications. So that is one of the very first things that we have to decide whether we're doing traditional or model. And again, traditional is an injection time-based system. Essentially, we only have the fuel table values to alter and the master fuel trim, which is essentially an overall fuel trim to alter, to get the pulse width to where we want it to be to get the fuel into the engine and to dial our engine in. The model, a lot more factors and variables we have to enter in, but it does give us, in my opinion, superior control in most cases compared to the traditional. And we also have the added benefit of being able to quickly set up a base table, getting almost any engine up and running, as we'll discuss in future model specific training tutorials. So hopefully this makes sense as to how this is going to work and the details that we really need to know. Traditional, super simple for injection, getting everything dialed in and set up. Model, a little bit more complex, but offers a lot greater control, and it does have, again, a lot more benefits that are built into that math modeling that we will starting to peel back the layers on that in future training tutorials and training modules. That's going to be it for taking a look at the basic overview of the traditional versus the model mode.
Thanks for watching our tutorial. If you're interested in learning more about how to tune your Link G5 or G4X system, check out the video description below where you can find links to our school, some promo codes to get you started and save some money. If you're interested in learning more about Link engine management products, also check out the video description below. That's going to wrap it up here. I hope to see you guys in our school.